अच्छा, तो लास्ट टाइम ने क्या किया था? We did entropy and I told you disorder, high entropy, low entropy. I explained that high entropy states are the more probable, the more stable states. Like if I shake this glass jar, it's going to maintain its state. This state is not going to maintain itself. So that's a low energy state. It requires very little energy to achieve this state. It requires a much bigger energy to reach an ordered state. Okay, so high entropy is like the more favorable state. So change in entropy positive, that means gain of disorder, that's easy. Loss of disorder difficult. Solids less disorder, liquids more disorder, gases a very high entropy. तो हमने थोड़ा सा किया था कि qualitatively figure we try to figure out how how to predict what the entropy change is, positive or negative. ठीक है, वो सारा clear? Is that clear?
Yep.
अच्छा, अब ये कि this is change of state, so disorder increases. Now we're going to move towards the mathematical stuff. First one, how do you calculate disorder? Okay, that's number one. Just a second. So formula for delta S. What's the formula? How do you measure disorder? That's a question. So the way you're going to measure disorder is, and we're talking about chemical disorder over here. Entropy has many different applications in the real world. Okay, last time I explained to you why entropy was important, because whenever entropy increases, there's a gain of disorder, and that produces work. So I explained to you that systems, they don't produce work because of enthalpy change. Like burning a mass produces heat, but you don't get much out of it. But lighting up वो क्या होता है, fire, like lighting up a firework, that produces a lot of work. So disorder created, that produces work. So whenever we look at a reaction, we focus on the disorder rather than the enthalpy change. I explained to you that car engines ke andar na, you burn octane. You don't burn octane because it produces heat. That heat is irrelevant. The advantage of burning octane is that it produces a lot of small molecules. It creates a lot of disorder, and that disorder helps in the movement of the piston. So systems, they operate on delta S. Is that clear? So whenever work gets produced, delta S is positive. Is that clear?
Yep.
So based on this thing, we're going to figure out what the formula is. So the formula is simple. So the formula is entropy change is the work produced at a particular temperature, or at a fixed temperature. That's what entropy change is. The work produced is in joules, and this is in kelvins. So whenever there's a gain of disorder, let's say steam gets produced, right? So if steam gets produced, there's going to be work produced at a particular temperature. Temperature is important because steam, jo na, water liquid, it's not going to do any work if it's at minus 10 degrees centigrade. So entropy kya hogi? Low hogi. Does that make sense that at minus 10 degrees centigrade, it's going to have low entropy? Why? Because it's not going to produce any work. The piston is not going to move up at minus 10 degrees centigrade. But if it's at 120 degrees centigrade, disorder is going to be created, and that is going to produce work. So work is going to be produced at a particular temperature. So temperature is important because the temperature is what is going to define whether work is going to be produced or not. So is that clear? Does that make sense?
Yeah, it does.
So that's your formula for delta S. It's work produced at a particular temperature, and it's often written as delta S is equal to minus delta Q. That's the work that is produced. The minus sign is there because it's exothermic. When delta S is positive, I said delta S and work produced or Q have opposite signs. Reason being that delta S positive means that means there's a gain of disorder. That means work is going to be produced. That's exothermic. So that's why you have a negative sign. So Q heat or the work produced and entropy change, they are have opposite signs to each other. Is that clear as well? Yeah.
Yeah.
Okay, so and the unit for standard entropy is per mole. So it's going to be joules per Kelvin, or simply, I mean, joules is J. It's going to be J per Kelvin per mole. And you have entropy changes calculated for different substances at different temperatures. Like if you have oxygen gas, if oxygen gas is at minus 200 degrees centigrade, it's probably going to produce little work. There's not going to be a lot of disorder. If oxygen gas is at 1000 degrees centigrade, it's going to produce a lot of work at that particular temperature. So, so it's work produced at a specific temperature. That's the formula. और इसको हाईलाइट करते हैं इसमें joules per Kelvin per mole. So the other thing about this is that that's a formula for delta S. The other thing about this is it's you're not really going to use this formula. Standard entropies for different substances are already calculated and given in tables. So the formula just represents how it's done. So standard entropies for different substances are already calculated. So you're not interested in standard entropy of different substances. What you're interested in is the delta S for a reaction, or the entropy change for a reaction. If you know the entropies of your reactants and products, then you just have to take the difference. And that's it. Because so that's basically your formula. So if you know the product entropies, you know the reactant entropies, just subtract them and you'll get the entropy change of that particular reaction. Is this clear?
Yep, it's clear.
We'll just do questions on this. Okay, that's your next formula. So we're gonna do some questions. 1 second. I said not notes. Where's the I said so for example, this one. The entropies of your products is already given. The entropies of your reactants, that's also given. So you just have to take a difference. So product entropies, what are your product entropies? Silver ions, that's 72.7. Cl ions, do you have a calculator? 56.5. And minus my reactant, which is EgCl, that's 96.2. Okay, what is the difference that I'm getting?
Could you give me a second while I go and get my calculator?
ठीक है.
The answer is 33.
अच्छा इसका अच्छा this one is 33. So next one. So most of the questions are going to be like this for this part. Just a second. Can you calculate the entropy change for this reaction? So product minus reactant. So product is int 192 divided by 2. O2 is what, 205 divided by 2. I2 is 261 divided by 2. And 2 water, that's 70 times 2. Minus NH reactant, that's so minus 42.
557.5
500.
and 57.5.
Okay, so that's it. So the other variation of the question will be that they'll give you delta S and they might ask you for entropy change of a particular reaction. So not this one, this one. See, this one is kind of the same. Entropies are given, so product minus reactants, you'll be able to figure that out. इसका क्या आ रहा है? बस एक और कर लेते हैं. What is this? EPO, that's a product 69 times 2. O2 is 205. Minus 77 times 2. What did you get for this?
189.
So you're getting 189. So not really much of a variation in this. This one is the reverse. You can just let's do this one, the last one. So delta S is already given. So you know what delta S is? 225.7, right? So it's the entropy of the products. So SiCl4, that's given, I think. Yeah, that's given. So that's 239. Just once minus my reactant, which is Si, which is 18.7. And Cl2 is not given, so that is 2x. Okay, you just have to find for it. You have to solve for x now.
223.
So 223,
Not
right?
as much.
Okay. So okay, that's it. The simple formula, product minus reactants. That's it. Okay. So now the last thing. So you can figure out entropy change. The entropies would be given to you. That's about it. Now, what we're going to do is we're going to talk about the Gibbs free energy. ये एक सेकंड में स्पेसिफिकेशंस के अंदर ना लेट मी जस्ट किधर है AQA 1 second where's ठीक है this one gives free energy the rest we covered right here just this one entropy change we already did that अच्छा now gives free energy is it's known as delta G अच्छा now what this energy it's a net energy that's available to a system for useful work. I said to do useful work. So for example, so net energy available to do useful work. So the thing is that you've got a system or a chemical reaction. Now a chemical reaction produces energy in two ways. So one way it's going to produce energy is that it's going to produce. I mean, like if you burn petrol, right? So one way of producing energy is that that is heat energy. So it's the heat energy that's produced. And the other way, the more important way of producing energy, okay, the one that we are more interested in, that's sorry. So that one is the work produced by entropy change. Okay, so the system does or produces energy in two ways: heat energy and the work produced by entropy change, right? And the more useful one is the amount is the work that is produced due to entropy change. That's more important to us. So that's your overall energy of a system. ठीक है कि कितनी energy वो produce कर रहा है. Now the thing is, let's say I have this reaction, water liquid, and that water liquid is turning. So that water liquid is turning into gas. So do you think this reaction produces work or energy? क्या होगा? Will it produce energy or not?
Yes.
In what way? Like, will it produce heat energy or will it produce the work that happens due to entropy change?
Will it produce both of them?
The
Or can it only produce
liquid
one?
water to gas, is that exothermic or endothermic?
Is it endothermic?
That's an endothermic. So it's not going to produce any heat energy, right? So it's an endothermic reaction,
Okay.
right? So endothermic, so that means it needs heat energy, right? But if this happens, there's going to be a lot of entropy change, right? So that means delta S is positive. That means there's a gain of disorder. And I told you that whenever delta S is positive, that means work is produced. The piston is going to move and it's going to expand and it's going to be doing work against the environment, right? So the system is consuming energy in terms of heat, but it is producing energy in terms of entropy change, right? Is that clear?
Yep.
So what do you think? So Gibbs free energy is the net energy that's available to the system. So what do you think? Um, is this a? Do you think it's a feasible reaction, spontaneous reaction? Does it have enough energy, or does it need energy? Like it just common sense. Like, will this reaction, this particular reaction, let's say you've got a piston and it's got liquid water in it, right? Will this reaction happen at minus 50 degrees centigrade?
No.
It won't be able to produce work, right? Why?
No.
Because it needs heat energy, right, to turn into gas, right? So at what point do you think the reaction will be spontaneous? At what temperature do you think this reaction is spontaneous?
100 degrees.
So that means the reaction will happen spontaneously if the system has a temperature greater than 100 degrees centigrade, right? Because then it will turn into gas. I said then it will turn into gas. And at the same time, when it turns into gas, it's going to produce work due to entropy. So that means at temperatures above 100 degrees centigrade, it does not need extra energy from outside, because at 100 degrees centigrade, it's got sufficient energy to do everything on its own. That means at temperature greater than 100, its total net energy, the Gibbs free energy, that's exothermic, that's negative. That means it's got sufficient energy. Negative means that it's got sufficient energy where it does not need energy from outside. Is that clear?
Yep.
But at temperatures lower than 100, the system will not produce any work. Why? Because it would need energy from outside. Because if it's at 10 degrees centigrade, you would have to give it energy first, turn it into gas, and then it will be able to produce work. So that means the net energy will in that case be positive. That would be in endothermic. So the main idea is that if your delta G comes out to be negative, that means reaction is spontaneous. That means it's got sufficient energy, no help needed from outside. Vice versa, if your delta G happens to be positive, that means it's non-spontaneous. Unless it gets that energy, it's not going to happen. अच्छा तो इसका इस पे आ जाते हैं. Let's say the burning of octane in the car engine, right? You burn it, it's an exothermic process, so that means it produces heat. That is one form of energy. And when you burn it, it produces a lot of small molecules. That means delta S is positive. That means work gets produced. So, will this reaction in any case be non-spontaneous? But in हर case where it's producing energy, right?
Yeah.
So it produces heat energy every time, no matter what the temperature is. And no matter what the temperature is, you burn it, it's going to produce a lot of small molecules. So there's going to be delta S positive. So that means it will produce work at all cost. So no matter what the temperature is, this reaction will be spontaneous in all conditions. The surety is that, so that's the idea of Gibbs free energy, that it's kind of the sum of whatever available useful energy that you have. The formula kya hoga? It's basically a sum of these two energies, right? The total energy that's available. So the formula that we can come up with is the delta H is basically equal to the heat energy that's produced plus the work that is produced due to what delta is, right? So it's the sum of these two things. Now we know for a reaction that heat energy is basically enthalpy change, right? And how do you calculate work produced due to delta S? That is basically equal to minus T delta S. I'll explain that. Like where did I get that? Just 1 second. So to sum it up, your delta G is basically equal to delta H minus T delta S. So where did I get this T delta S? I got it because earlier I had explained if you know what entropy change is work produced at a particular temperature. So if I rewrite this, what is the work that is produced? That is basically equal to minus T times delta S if I rearrange this. Is that clear?
Yeah, it's clear.
Because that's where I'm getting this. So that's the work that is produced due to entropy change. So that's my formula, which I'm going to use. Because that's the sum of enthalpy change plus plus the work that is produced due to entropy change. That's it. So and remember delta G coming out to be, so if delta G comes out to be negative, I mean this part is also important. Negative means that it's spontaneous. And positive means that it's non-spontaneous. अच्छा अब ये सारे अब इसकी यूज ठीक है. One is qualitative, the other one is quantitative. So for example, if I give you a reaction, I'm going to use delta G now, ठीक है. अच्छा, what do we want? Do we want delta G to be negative or positive? मतलब हमारा target क्या है for any reaction? Do we want it to be negative or positive?
Negative.
We want it to produce work, right? We don't want it to consume work. We don't need that. Because most thermodynamic systems are used for producing work, whether it's a steam engine, whether it's a car engine, or anything, any other thing. So we want it to be as negative as possible. So that's the whole task. We have to basically try and make this negative. तो बताओ कि वापस उस पे आ जाते हैं कि I've got water which is liquid and I've got it's turning into water gas. पहले तो just we obviously know it's a common sense. When is this reaction spontaneous? High temperature or low temperature?
High temperature.
Yeah, we know it's so that means at high temperature, it's going to happen on its own. Like if it's 1000 degrees centigrade, you don't need any help from outside because you're already at 1000 degrees centigrade. It's going to happen spontaneously, very, very quickly, right? So, how do I justify this statement, which is, I mean, just common sense? How do I justify it using this equation over here? So, the delta S for this is that the disorder is increasing, so that's positive. The enthalpy change for this reaction is also positive. It's an endothermic reaction, right? So, both of them are positive. So, I'm going to plug them in the delta G equation, which is delta H minus T times delta S. Now, if I plug these values over here, delta H is positive and delta S is also positive. But because of the negative signs, one of the term actually becomes negative. ठीक है, remember I told you कि अगर delta S positive होता है, work is produced. So that means exothermic. Delta S and work had opposite signs, right? So if delta S is positive, because of this negative sign, you automatically get a negative value on this side. So one side is negative, the other side is positive. Now, if I want to make this reaction spontaneous, right? I want to make this negative. That's the whole task, right? तो मैं कौन सी टर्म को बड़ा करूंगा, ठीक है? I would have to try and make the negative term larger, right? And how can I make the negative term larger? The only way I can make the negative term larger is if I have a higher temperature. Then this negative term would be, I mean, the only thing that you can change that is under your control is temperature. So you can increase the temperature, the negative part would become larger in size. So overall delta G would actually come out to be negative. Is that clear?
Yeah.
Or common sense be, okay, this reaction will happen at a larger temperature, right? So the common sense was that this reaction will happen at larger temperature, right? So there's a lot of questions that will be qualitatively handled where you just have to guess whether something will happen at lower temperature or higher temperature. So, अच्छा इसका बता दो कि let's say we do another one. Water ही ले लेते हैं. Let's say liquid to solid, right? अब common sense कहती है कि I mean this will happen at a lower temperature, right? It's going to be spontaneous at a lower temperature. So how do we justify it using Gibbs free energy? So the enthalpy change for this reaction, is this exo or endo? क्या चीज है ये?
Ender, exer.
Yeah, this one is exo. Liquid molecules would lose energy, right? So
Yeah.
तो ये वाला part जो है ना, that's negative. And what's delta S for this? Positive or negative?
Positive.
Yeah, you sure there's a gain of disorder or loss of disorder?
There's a loss of disorder.
So that's negative, right? There's a loss of disorder, so that means disorder decreases, right? Is that clear?
Oh yeah.
So both of them are negative, right? So I'm going to plug these values in my delta G, which is delta H minus D delta S. So delta H is already negative and delta S is already negative. So two negatives would actually make a positive. So actually this part is actually, so one of the terms is negative, the other one is positive, right? So if I want to make delta G negative, so that means the negative part must be larger and the positive part must be smaller in size. I can't really do anything with delta H, but the only thing I can change is temperature. So what I can do is I can use a smaller T. So if I use a smaller T, the positive term becomes smaller in size. So overall delta G would become negative. Is that clear?
Yep.
Or automatically na wo, and that was what we learned. Common sense says it is feasible at lower temperatures. Ice is formed at a lower temperature, right? So clear qualitative use clear.
Yep, it's clear.
Now further we can sort of now apply to other reactions like the Haber process. And let's say I'm just talking about the forward reaction. The enthalpy change is negative. It's minus 88. I mean, right now, no calculations, just that it's negative, right? अब खुद figure out करो कि will this be spontaneous at higher temperature or lower temperature? Try and figure this out. I'll you pull example that's in front of you.
Is it lower temperature?
I said lower temperature. And how did you figure this out? What is delta S?
Negative?
Okay, so there's a loss of disorder, right? So that means both are negative, right?
Yep.
So now if both are negative again, I need to make delta G negative. So both are negative. That means this actually is positive. So I need to get rid of the positive term. So because I want delta G to be negative. So T would be kept as small as possible. To be negative, right? Is this clear? What
Yep.
is so can you plot a table? What you're going to do is this is your homework. So plot a table where you have let's say I write the sign of delta H, I write the sign of delta S for a particular reaction, and you figure out when is delta G less than 0 at what temperatures. जैसा ये negative negative का तो आ गया ना कि if both of them are negative, like in this question, then delta G will be negative only if T is small. Is that clear? Is this
Yeah,
clear?
sounds good.
So we're just gonna just fill in the table. If this is negative, this is positive. So, I mean, answer this. What happens to this? Like, when will delta G come out to be less than 0? Then if this is positive and this one is negative, when will delta G be less than 0? And third one, the last one is if both of them are positive. तो ये ठीक है ये try and submit this ठीक है probably today छोटी सी exercise है that's it.
Okay.
So I mean try and do this in the next 10 minutes ठीक है.
Yeah, okay.
So ठीक है मतलब we'll talk on Friday then ठीक है.
Sorry, regarding the class timing, so are the days gonna stay the same? Saturday, Sunday, and Friday, Saturday, and Tuesday,
Yes.
or can we
Um,
interchange?
which day do you want to change to?
I'd rather do weekdays, if that's okay with
Saturday,
you.
we can take out Saturday. We can do it tomorrow.
Yeah. So Monday, Tuesday, Wednesday.
Do we have a? We don't have anything on Monday.
No.
Yeah, Monday, Tuesday, Wednesday is fine. That's fine.
Is that fine? Okay, at 6 o'clock, the same time.
Yes. I mean, we can have class tomorrow. Today's Tuesday, right?
Yeah, today's Tuesday.
So we can have class tomorrow as well.
Okay.
Okay, we can have class tomorrow because we didn't have class on Monday. So we can have class tomorrow and then
Or if it's easier for you, can we have one day where we have a class of that's a bit longer? So then it's less days, but
hey,
one day will be
that would
longer.
probably not be possible because it's already very late. So we can
Okay.
I mean that can be possible if it's that's a possibility.
Maybe if on Sunday, because then